with your video on your vector valued functions. So, and it's not very much different than parametric equations, to be honest, as you'll see. A vector is a directed line segment. Oh, and I will post this sheet as a PDF when I do the update as well. If you have a printer, you can print it. If not, then you can just watch this video. And I can give you a copy when we get back to school. Directed line segment with direction and magnitude, which is how far it has gone. So it has direction and it has a length or distance. And I'm going to link this too because I think of it every time and I think it's funny. And if I'm the only one that thinks it's funny, that's okay. But if you remember the first Despicable Me movie, if you've seen those, like Despicable Me, the first one, the villain's name was Vector, and he's like, I'm committing crimes with direction and magnitude, and it's just funny, so I'm gonna post that. So, all right, your magnitude is written like this. Looks kind of like an absolute value, but double bars. And it is literally just, if you remember from geometry class, which I know it's like, I'm school, of course we don't remember from geometry class, but it's literally just your distance formula. And the other thing that you can relate it to is the arc length that we did recently. The only difference is there was an integral at the front and a dx or a dt at the end. And it was x prime squared plus y prime squared. All foundationally comes from the same place. All right, so, and you can see vectors written as like a V with like a little arrow on top, or they can just be bolded. Here I just have them bold. But you can also like see it just written like that too with a little arrow above it. All right, so our first vector starts at the point 0, 0, goes to the point 3, 2. Vector u goes from here to here. Show that they are equivalent. So I'm going to kind of work with v over here and u over here, and we're going to show that they have the same magnitude and direction. So first, let's find magnitude. Big square root. We're going to subtract. So 3 minus 0 squared, and then plus 2 minus 0 squared. I know you can probably do some of that in your head, but just trying to show everyone the problem. Be 3 squared plus, oops, that's a horrible 9. 3 squared plus 2 squared, and so we get square root of 13. So I'm going to do the exact same thing with these 2 points. And so for the first one, we have 4 minus 1 squared, and then 4 minus 2 squared for our y values. And again, you'll see it's going to come out to 3 squared, which is 9, 2 squared, which is 4, and square root of 13. So they have the same magnitude or distance. How do we show that they have the same direction? That's going to be if they have the same slope. So we're going to find the slope for each of them. So y2 minus y1 over x2 minus x1. So this one will look like this, comes out to 2/3. And then this one would be 4 minus 2 over 4 minus 1, which also comes out to 2/3. So we showed that they are equivalent. If you also want a picture, I usually like a visual. First one goes from 0, 0 to 3, 2. And you just show it with an arrow like that. So your initial point and your terminal point. And then the other one starts at 1, 2 and goes to 4, 4. And if my picture is fairly decent, you can see that they have the same slope and they're going, the same distance. Mine's not very great though, but I didn't have a grid. So, but basically if you pick this one up and move it over, it would sit right on top of this one, which is actually the next thing that we're going to look at. A component form simply means that your vector begins at the origin. So you can write the component form of a vector. So the component form of this one is this one. And it's written with, instead of parentheses, it's kind of like a pointy parentheses. So we have V1, V2, and that's how you're going to see it on the AP exam. I've never seen it this other way, but if some of you have heard of this, you can see it with like an I and a J. I am never going to write it that way. I'm only bringing it up in case some of you have seen it before. We're going to write it this way. So it looks like a coordinate point, like parentheses, except they're pointy. So it's where your initial point is the origin, and your terminal point, which is where you end up, is whatever those two numbers are. Okay. So again, the one we did up here, the component vector of this one is this one. You just force it so that it starts at the origin. It's a whole lot easier to talk about when one of your points is 0, 0. Zeros are just easy numbers. It's an easy number to deal with. So find the component form and length or magnitude of the vector that starts here and goes to here. So basically all we need to do for our x dimension is figure out how this changed. How far did we move in the x direction? And you can kind of just imagine a number line. If you go from 3 to -2, you went -5. Again, just think of a number line. If you're on your number line, it's 3, and then you end up at -2, you went -5. Or you can think of like you're going to the left. And we're going to do the same thing with the y's. If we go from -7 to +5, we're going positive 12 units. So it's just how you got from this point to this point. Basically, your component vector is instructions. It's how you got from here to here. What did you do? Well, we went left 5 and up 12, essentially, is what we did. All right, so let's find our magnitude. It's going to be this square root of -5 squared plus 12 squared. So that is going to be 25 plus 144. That is square root of 169, which is 13. And again, if you like a visual, these always end up being, triangles sort of. If you start at 0, 0, and you go left 5 and up 12, you end up with this being your vector. If you want to think of it as a triangle, though, it is a 5, 12, 13 triangle. That's one of your Pythagorean triples. But this distance or magnitude is going to be 13. All right. For our component vector, -1, 3. And again, just try to think of this as instructions. You went left 1 and up 3. Initial point is 4, 2. What is the terminal point? Well, I'm just going to take where I started and use this as my roadmap or my instructions. So I'm going to subtract 1 for my x and then add 3 for my y. 2 plus 3 is 5. I'm not going to read all these to you. I took a picture of a textbook and put this on here. These are all of the different things that you can do with vectors and all of the properties that they follow. And again, you probably can't see this too well, but I'll give you this sheet when we get back to school. But it's just saying you can scale vectors, which I'm going to show you on the other side of this, meaning you can multiply them. You can add them to each other. U plus V equals V plus U. That's your commutative property. They follow all these properties. Basically, all of the common sense things that you think would work with vectors do work. So here's what it looks like if you scale them. We have vector V and vector U. We're going to do 1/2 of V. Literally, you're just going to take these two numbers and halve them. Just divide them by 2. So it's going to be -1 and then 5 halves, or 2.5. Here we're going to do U minus V. So I'm going to do 3 minus -2. That would be 5. 4 minus 5 is -1. All right, we're going to do V plus 2U. So for our x dimension here, that would be -2 plus double that is 6. So that would be 4. And then we're going to do 5 plus doubling. This would be 8. So 5 plus 8 gives you 13. So you're just allowed to do all of those operations on vectors is all that that's saying. All right, so a component vector means you're starting at the origin. A unit vector causes the magnitude to be 1 unit. It's basically like forcing it to be kind of like the unit circle, if you want to think of it that way. But it forces the magnitude to be 1. So we want a unit vector that's in the same direction as V, as the vector we start with. You just take that vector and divide it by the magnitude. So, and I'll draw you a picture to show it to you as well. So find the unit vector in the same direction here. Well, first thing we have to find is the magnitude. So let's go ahead and do that. We're going to have 8 squared plus 15 squared. It's going to be 64 plus 225. Oh, said it correctly. I just didn't write it correctly. So that is going to come out to 289, and the square root of 289 is 17. That's another one of your triples, 8, 15, 17. 3, 4, 5 is another common one. And you got 7, 24, 25. There's a bunch of them. So our unit vector, we're just going to take this and divide it by 17. So 8 17ths and then 15 17ths. is our unit vector. So here's a picture of what that would look like. I'm going to draw both of them. I'm going to draw the original one and then the unit vector. So the original one, we go 8 in the x direction, 15 in the y direction. And if you drawing this triangle, here's your vector. We have 8, 15, and then the hypotenuse is 17, kind of just getting back to some geometry here. The unit vector forces that magnitude to be 1. So what ends up happening is this is 1 unit, and our x dimension is now 8/17, and our y dimension is now 15/17. So again, it takes this and it makes it the exact same thing, exact same direction, but it forces your magnitude to just be 1 unit. That's why it's called a unit vector. All right, so we want to find a vector with a magnitude of 9 in the same direction as this one. So I would start with a picture for this. I'm going to go ahead and draw that same as I drew these triangles here. We're going to go left 1 and up 2. So our vector is going to look like this. And if I draw in my triangle, I know it's -1. I'll just stick the negative in there. And then up 2. So if I go to find my magnitude of that, and it's the same formula that we've been doing the whole time. It comes from the Pythagorean theorem is really what we're doing. We're going to have -1 squared plus 2 squared. What is that? 1 plus 4 is 5. So this is square root of 5. Right in there. I didn't draw that very well. Let me make that a little bit clearer. So that's square root of 5 is the magnitude of our vector. But it says that the directions say that we want our magnitude to be 9. So we want it to be the exact same thing, but for our magnitude to be 9. So basically, we're just scaling it. How did we get from here to here? So it's like, what did we do to square root of 5? We multiplied it by, what to get 9? And you would just divide this over. You have to multiply by 9 over square root of 5. You take this and multiply by 9 over square root of 5, you're going to get 9. So I'm just going to take my x and my y dimensions and multiply them by 9 over square root of 5. So for my x dimension, that's just going to be -9 over square root of 5. And then here, if I multiply that by 9 over square root of 5, it's going to be 18 over square root of 5. And so what we did there is we created a vector that is in the same direction as this one, but I changed the magnitude. Instead of square root of 5, now it's 9. So we just changed it to what the problem said to make it. All right, and then last one, we are going to do a little bit of unit circle here. We want to find a vector with a magnitude of 2, and we want the amount of rotation to be 5 pi over 6. So I'm going to start by drawing that. 5 pi over 6 is in your second quadrant. If you go 5 pi over 6 amount of rotation, your reference angle is pi over 6, or you could think of it as the whole 6/6 will get you to 1 pi. But this is our vector, and I just drew in the rest of the triangle there. Let's review some unit circle. The hypotenuse would be 1, so our magnitude here is 1. 1/6 of pi is a tiny slice of pi. Across from the smallest angle, you have the smallest side. And the choices for your sides are 1/2 square root of 2 over 2 and square root of 3 over 2. The 1/2 and the square root of 3 over 2 go together. This one's going to be negative because we're in the second quadrant. Just to review unit circle a little bit more, if this was pi over 4 as your reference angle, then both of these would be square root of 2 over 2, except that one would still be negative. All right, now we don't want our magnitude to be 1, though. We want our magnitude to be 2. So we're going to do the exact same thing that we just did above. I want to change this 1 to a 2. Now, this one's actually easier than the one we just did. All I'm going to have to do is double everything. So this would be 1, and this would be negative square root of 3. So this would be our answer.